Deterioration, Identification, and Rehabilitation of Pre-Stressed Concrete Piles by Natallia Shanahan from Vector Corrosion Services. So today I'm going to start by briefly talking about the corrosion mechanism and the marine exposure environment. And then I'm going to use Tunny Bridge as my example for evaluation and rehabilitation. We're going to talk about the bridge substructure, assessment of the piles in terms of for corrosion, and cathodic protection for the piles. And then we're going to finish up with some conclusions. So I'm sure everybody is familiar with corrosion and the effects of corrosion on reinforced concrete structures. To have a corrosion reaction, you have to have four different components. You need moisture, oxygen, a metallic path, and that's reinforcement, and an electrolyte. So in concrete, the electrolyte is the concrete pore solution. I'm not going to bore you with the chemistry, but in a corrosion reaction, you have an anode and a cathode. The anode is where corrosion is formed. You have the formation of rust, and there is no corrosion, no section loss occurring at the cathode. But to have a corrosion reaction, you have to have both an anode and a cathode. In a marine environment, corrosion is caused by penetration of chloride ions from the seawater to the reinforcement depth. In new concrete, reinforcement is protected by the naturally high pH of the concrete pore solution, which causes the formation of a passive film on the rebar surface. But as chloride ions migrate into the concrete, they break down the passive layer and corrosion initiates. Corrosion causes a lot of damage to the concrete itself because corrosion products occupy up to 7 times the volume of the original iron metal. So when corrosion starts, corrosion products build up on the rebar surface. They create tensile stresses inside the concrete. These tensile stresses causes cracking. Cracks form over time, become delaminations, and delaminations spall. And this is the typical progression of corrosion. In bridges that are exposed to marine environments, the element that's at the highest risk for corrosion is the substructure. Corrosion risk for the substructure can be further divided into 3 different zones. The submerged zone, that is always underwater, the tidal splash zone, and the atmospheric zone. So in the atmospheric zone, there is no direct exposure to the water spray. But in the tidal zone, we have cycles of wetting and drying, and because of that, this is the most severe exposure environment. Also, in the tidal zone, there is high oxygen availability. And the repeated cycles of wetting and drying actually draw chlorides in to the concrete at a faster rate. In the submerged zone, the exposure is less severe, so even though we still have high chloride exposure, there is less oxygen availability. So corrosion still occurs, but at a lower rate. And in the atmospheric zone, there is a much lower chloride exposure. There is no direct exposure to salt water, but you still have an exposure to chlorides because of aerosolized salts. So wave action sends chlorides into the air. These chlorides settle down on the concrete surface, and over time they will penetrate into the concrete and can cause rebar corrosion. However, in this area, because it is dry, corrosion will progress at a slower rate. Tunny Bridge is a good example of a marine bridge. It is located in New Jersey and connects Toms River to Seaside, New Jersey, and that's the famous Jersey Shore. This bridge was constructed in 1969. It is a very long bridge, just under 4,900 feet. It has 50 spans, and the deck is supported by precast, pre-stressed girders that are supported by bents with precast, pre-stressed cylinder piles. As you can see in this photo, there is a notable change in elevation between the abutments and the middle of the bridge to allow ships to pass under the bridge. There's 4 different types of bents on this bridge. They have from 3 piles up to 6 piles in each bend. And here is a design detail for the precast pre-stressed piles. So these piles were hollow. They have a 5-inch thick wall, and the cover depth specified in the original drawings was very shallow. It was only 1 inch and 3/8, which especially for a marine environment, as we know now, is a very, very shallow cover depth. The piles have 24 pre-stressing strands. They're 54 inches in diameter, and there's also spiral reinforcement that's a 1/4 inch. So a recent inspection identified widespread cracking in the piles. The width of the cracks ranged from hairline cracks all the way up to 1/2 inch. So New Jersey DOT engaged WSP to provide an evaluation of the piles and to come up with a rehabilitation. And WSP reached out to VCS to assist them in the corrosion evaluation and corrosion mitigation. The structural engineer selected a sample of 24 piles. As you saw, that bridge is very long, and it was just not practical to look at every single pile. So the 24 piles ranged in the crack width. And our inspection methodology consisted of ground penetrating radar survey, electrical continuity testing, corrosion potential survey, concrete chloride sampling. We performed openings as well, and we did carbonation testing. Ground penetrating radar is an undestructive electromagnetic method of locating reinforcement and determining cover depth. Cover depth is extremely important to service life. As you can see in the equations below, the top equation shows you the time to chloride-induced corrosion initiation, and cover depth X here is squared. And the equation below shows the time to initiation of chloride-induced corrosion, and the cover depth D here is squared again. We knew that the cover depth from the original drawings was rather shallow, but as we know, what was specified and what's in the field can vary, so we wanted to verify what the actual cover depth was. And it was pretty close to the specified. The average cover depth was 1.3 inches, and the standard deviation was 0.2 inches. The electrical continuity testing showed that in each pile, about 50% of the strands were electrically continuous. And we also did corrosion potential testing on all the piles. This is also known as half-cell testing. And that's done to ASTM C876 to determine the probability of active corrosion. In this test, a positive lead from a voltmeter is connected to the reinforcement, and a negative lead is connected to a copper sulfate reference electrode. And that reference electrode is placed on a grid along the surface of the concrete element. And at each testing location, the potential is recorded. ASTM 876 provides an interpretation table for the potential measurements, which you see here. So ASTM says that anything that is more electropositive than negative 200 millivolts is at 90% probability of having passive steel, and anything more electronegative than 350 millivolts is at 90% probability of active corrosion. And between these two values, the probability of corrosion is uncertain. So based on the corrosion potential surveys, we created heat color maps for each of the piles, and I picked 2 representative ones here. It shows one of the shorter piles and the longer pile. So what we saw was that on the shorter piles, there was active corrosion pretty much for the entire length of the pile. And for the longer ones, in about 2 to 4 feet from the top, the reinforcement was passive. This figure shows the results of chloride concentration testing. Here, the red line that you see is the corrosion initiation threshold of 350 ppm. The vertical green line is the average cover depth for the reinforcement from the GPR, and the dotted green lines are plus or minus 1 standard deviation. And these profiles are chloride concentrations with depth. So as you can see here, all the samples had very high chloride exposure. At the surface, chloride concentration ranged from about 4,000 to 7,000 parts per million. And as expected, chloride concentrations decreased with depth. However, at reinforcement depth, concentration was still above the corrosion initiation threshold. We also did carbonation testing, which you see here. So a carbonation test is when you expose a fresh surface on the concrete and spray an indicator solution. If the indicator color turns purple or pink, as you see in this photo, this means that concrete pH is high and concrete is not carbonated. If there is no color change, that means the concrete is carbonated. So in this case, we did not see any carbonation. And the most important test that we did was the openings. Before we went out there, there was a big question from the structural engineer as far as how much section loss does the reinforcement have at the cracks. So when we did the openings, what we saw was that at the cracks, regardless of the crack width, we did openings on piles with cracks ranging from 1/8 of an inch to 1/2 an inch. The spiral reinforcement was completely severed. And this is what you hope you can see here. So these are the ends of the spiral reinforcement that just stop. They look like they have been completely cut. So where typically corrosion causes a buildup of corrosion product, this did not happen here. And this is because in the marine environment, we have water movement through the cracks. So as the water was moving in and out of the cracks, it was washing out the corrosion products, which resulted in complete section loss with no delaminations whatsoever. Also, as the corrosion products were being washed out, this exposed a fresh steel surface. So that itself increased the rate of corrosion as well. So for corrosion mitigation, we recommended installation of galvanic cathodic protection jackets. You see a schematic of the jacket here. So what you have in the jacket is an FRP or PVC jacket, which is essentially a stay-in-place form. The jacket allows you to do a cathodic protection and a concrete repair in one step. So anodes are attached to the jacket. The anodes mitigate the corrosion. And then the jacket is filled with grout. So this grout will fill any cracks or spalls within the jacket. There were several considerations in selecting the type of galvanic anodes to go into the jackets. The DOT required that the jackets start immediately below the bend caps and extend all the way down to within 6 inches or 1 foot of the mud line. Because of the cracks, they wanted the entire length of the pile encapsulated. And pile lengths ranged from 9 feet to 34 feet. And this resulted in a combination of exposures for different piles. There were piles that were in submerged and tidal zones only, while other piles had areas that were submerged, tidal, and exposed to the atmosphere. So because of that, we selected mortar-encased, self-activated, distributed zinc anodes. And this is an example on the right here. Because the mortar-encased anodes have an activator in the mortar, they can remain active in the submerged, tidal, and atmospheric zones. So for the marine zone, we selected marine anodes, and they were also installed in the tidal areas. And for the atmospheric zone, we selected atmospheric anodes that can remain active in the dry atmospheric area. For the purpose of CP design, the jackets were divided into two categories: structural jackets, where additional reinforcement was designed by the structural engineer, and non-structural jackets that only needed cathodic protection. Within both of these categories, the jackets were further divided into subcategories based on whether or not they had atmospheric exposure. So here's an example of the design. These are the non-structural jackets. On the right, you see a shorter pile that only had submerged and tidal exposure. So you see here, the bottom of the cap was very close to the mean water line. That is right there. So for these types of jackets, we only used marine anodes. And then this is an example of a jacket for a longer pile with atmospheric exposure zone. The mean water line is here. So the marine anodes only extended 2 to 3 feet above the mean water line. And then atmospheric anodes were installed in the top portion of the jacket. You see that there is more anodes at the top. This is because the top of the pile had additional reinforcement. This shows the cross-section of the jacket. Inside is the original concrete pile. This is actually an example of a structural jacket. These are the anodes that are installed on the concrete surface. Then there was a welded wire fabric added for the structural jackets, and then the pile jacket itself. So for the structural jackets, installation of the jacket added 4 inches of additional thickness to the pile, and for non-structural jackets, it was 3 inches of additional thickness. The DOT also wanted every jacket to be monitored, so we installed monitoring boxes. Each monitoring box has a 0.1 ohm shunt right here, and you can see it in the actual box over there. And it also has a test connection, which is right there. So both the shunt and the test connection have bolts coming out. This is to allow the technician to collect the measurements without having to take the cover off the box. Jacket installation started in December 2021, and it is still ongoing. The cathodic protection criteria that is used for determining the effectiveness of the jackets on this bridge is NACE, which is now AMPP, SP0408, cathodic protection of reinforcing steel in buried and submerged concrete structures. So NACE says that you need either an instant off potential of at least negative 850 millivolts or more electronegative to achieve cathodic protection, or you need to have 100 millivolts of polarization. Based on our measurements, all the jackets so far have met the 100 millivolt polarization criteria. We also measured the current at each jacket. So initially, which is immediately after activation, and then after 24 hours. So the total average current measured at the shunt was 246 milliamps, but because the piles were all different lengths, a much better way to look at it, and this can provide comparison to CP criteria, is looking at it in terms of milliamps per square foot. So initial current was 18.5 milliamps per square foot, and then after 24 hours, the average was 8.8 milliamps per square foot. And this shows you an example of actual jackets under construction. The anodes that you see at the top that are lighter colored are atmospheric anodes, and the marine anodes are a darker color, which you can see there. This is the FRP jacket that was installed on the bottom of the pile, but not at the top yet. And these are the monitoring boxes. And these are the jackets after they have been completed. So to summarize, evaluation is key to understanding the health of the structure. You can have cracks that are not delaminating with complete section loss if you're in a marine environment and you have water moving through. So absence of delamination in the marine environment in the presence of cracking is not an indication that your corrosion reaction is at initial stages. Cathodic protection jackets can be used effectively to address deterioration of reinforced concrete piles, and using distributed anodes can provide CP in submerged, tidal, and atmospheric zones. And CP jackets are not just for marine environments, they can be used strictly in atmospheric exposure as well, with atmospheric anodes. Thank you for your attention. Do you have any questions? Yes.
Real quick, I apologize if I missed it, but how did you install that jacket underwater?
The jacket has a seam and it opens up. So it's just divers that go down, they open it up and they wrap it back around the pile. And then it has screws that go into the seam to close it up.
Very interesting talk there. So you showed that there was like 50% discontinuities. Mm-hmm. First, I'd like to know how you fix those. And then secondly, Raymond piles like that tend to have splices. And those splices are discontinuous top to bottom as well. So it'd be interesting to see how that was accomplished. And my third would be the crack width of an 1/8 inch to a 1/2 inch. Did it go all the way through the wall thickness?
Yes, some of them did.
How did you account for blocking that or filling those cracks? Because an 1/8 inch crack's probably not going to fill with the grout, but the 1/2 inch going all the way in, you might be filling that column up. Be tricky.
To answer your first question, if you see here, so the contractor started out by drilling holes to the strands to check for continuity, and then they decided that that's just not effective because they were finding that a lot of the strands were not continuous. They decided that it's much easier and faster for them to just chip out a groove all the way around the pile. And they brazed a wire all the way around to fix the continuity issue. And the second part of your question about splice piles, there's a continuity correction there as well. For the cracks, the structural engineer did not require any additional measures for cracks, so the piles were just pumped.
I had the same question about keeping the grout out of the inside of the pile. But also, does the anode have to be physically connected to the rebar, or does it work just attached to the outside?
Because these are monitored jackets, the anodes are not directly attached to the rebar. So the anodes are attached to each other, and then there is a wire, there's 2 anode wires. So right there you have the 2 red wires. So the 2 anode wires go into the junction box, and then the black wires are the structure wires. So the black wires are physically attached to the reinforcement inside the pile. And the anodes and the reinforcement is connected through the junction box. So this way, the anode current output can be monitored by, going through the shunt and having the test connection. Otherwise, you can directly attach them to the reinforcement. But yes, you would need to have reinforcement connections. But then you can't monitor.
So my question was, I'm not overly familiar with the carbonation thing you were talking about. So when you said that the purple or whatever shows that there's no carbonation, can you speak on whether that was a positive thing or negative or neutral? I'm just not familiar.
So what carbonation is a drop in pH of the concrete pore solution from the penetration of CO2 from the air into the concrete. This happens with time, and it happens to most structures, but you have to be in a particular relative humidity range. So if you're in a very, very, very dry environment, carbonation is very slow, and if you have a very high humidity range, carbonation is also very slow. Carbonation for the reinforcement is a bad thing because carbonation will drop the pH around the reinforcement, and that drop in pH will destroy the passive layer, and that will initiate corrosion.
Thanks, Natalia. For the overbuild condition where you're strengthening the pile, what was the surface substrate preparation in order to get a good bond and ensure the behavior that they were looking for?
So there is no bond between the welded wire fabric and the surface. It's, if you see here, it is placed after the anodes. So there's the original concrete surface, then the anodes are attached to the concrete surface, and then the welded wire fabric is placed around the anodes. So it's in grout, and it's encased in the grout that's inside the jacket, but it's not connected to the pile itself. So that was designed by the structural engineer. I wouldn't be able to speak to that. Thank you very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.